Now consider again the same box, but this time, and it's in a rocket which is accelerating with acceleration g. And we have a beam of light which we're going to shoot across the rocket. What will happen to that beam of light? Well, it starts out here, but as it travels across, the rocket has moved forward. And so now, by the time it gets here, it's at this point in the rocket. And by the time it gets to the other side, it's here. So what is actually happening? The light is of course going in a straight line, but because the rocket is going forwards, it appears that the light is actually bending downwards. So the net effect to an observer would be that the light starts here, it's then there, and it's then there. So in other words, it's bent, it's gone down in a sort of bendy circle as a consequence of the rocket moving. Well, that may seem pretty logical, and you might say, well, that's bound to happen. But Einstein said, but hang on a minute, I just established a principle of equivalence, that someone who's in a box on the Earth and someone who's in a rocket accelerating at g will see exactly the same thing. So if a person in a rocket accelerating at g experiences the light to curve, it must also follow that a person who is on the Earth who sees light coming through that box will see it curve. And that led him to the conclusion that light bends in the presence of a gravitational field. Now, at first sight, that seems rather surprising, since light consists of photons and photons don't have any mass. How can massless photons be affected by a gravitational field? But it was verified that this actually happens. During a total eclipse of the sun, where the sun had effectively been blocked out by the moon, there's the sun, here is the Earth, and what was noticed was that people on Earth could see a star out here, which, according to their calculations, shouldn't have been there. The star should have been here, and thus not visible because it was being blocked out by the sun. And what is actually happening is that the light from this star is being bent as it goes round the sun. And so it appears that the star is here, when in fact it is here. And that was the first experimental evidence that light bends in the presence of a gravitational field. The speed of light, of course, is invariant. It's a constant throughout the universe, or at least we think it is, of 3 × 10⁸ meters per second. So it doesn't change speed as it bends, but it does change direction. You might argue, well, what happens if the light is actually coming towards a massive gravitational object? Will that cause it to speed up? And the answer is no, but it will change its wavelength and it will change its frequency. And that's called the Doppler effect, and is very similar to the effect you hear when an ambulance or a police car or a fire engine goes past you in the street. As it's coming towards you, it has a very high-pitched tone. As it goes away from you, it has a very low-pitched tone. That's because the frequency of the sound is greater when it's coming towards you and is lower when it's moving away from you. Let's consider our rocket again. Here is our rocket accelerating at g, and inside it we emit a beam of light from the top of the rocket. Now, will that light reach this point here? Well, not quite in the way you think, but because by the time the light has reached the floor, the rocket will have moved up. And so the light which left here will eventually get to that point there. And it never gets to this point here because, of course, it will get stopped by the floor of the rocket, which is moving in this direction. And what happens is that inside the rocket, the waves get crunched up. In other words, they get a shorter wavelength. The wavelength gets shorter and the frequency increases. It has to, because c equals lambda times f. The speed of light is equal to its wavelength times its frequency. And if one of those gets shorter, the other has to get bigger in order to maintain the constant of c, the speed of light. So what actually happens in this situation is that if the rocket is going in this direction, then the wavelength gets shorter, and we call that blue shift, because blue light has shorter wavelength than red light. If, on the other hand, we were to take our rocket accelerating at g and send the light up from the bottom, then it would take, of course, a little bit longer, shouldn't need that bit there, to get to the top, because it's not just getting here, because the rocket has moved upwards, and so it now needs to go all the way up here. And that means its wavelength is stretched out. The wavelength goes up, so the frequency goes down, and that's called a redshift. So what Einstein said, well, if that's what happens when the rocket is accelerating with acceleration g, then according to my equivalence principle, that must be exactly the same as if the box were on the surface of the Earth, subject to an acceleration g, you should get the same effect. And so he concluded that where you have gravitational forces, they will cause the light to either increase or decrease wavelength, and you therefore get either a red or blue shift in the light in the presence of a gravitational field. Now let's consider an accelerating body. And I'm going to draw its position and its time in this way. We're going to have a graph which shows the time that has passed multiplied by its position on the x-axis. And this is an accelerating body. If it were a constant velocity body, then that would be a straight line, because the rate of change of distance with time would be constant, because you would be travelling at constant velocity. But if you're accelerating, then what we will see is a curve that goes something like this. And the reason is that as you accelerate, you get faster. And as you get faster, you cover more distance in a similar amount of time. So initially, you hardly cover any distance at all. But after twice the time, you've covered more than twice the distance. And after 3 times the time, you've covered significantly more than 3 times the distance. This is simply because you're accelerating and travelling faster for every second, and therefore you expect to get further as time goes by. Now here's the key. This is a curve. When you accelerate, you pass through space-time, which is what this essentially is. It's space measured on the x-axis, time measured on the time axis. You travel through space-time in a curve. And Einstein therefore says, and according to my equivalence principle therefore, if you are accelerating with, say, an acceleration g, that is the shape of the curve. If you are subject to the gravitational acceleration g, then your passage through space-time is also a curve. And that's what gave him the idea of curved space-time. And that's what we shall come to in subsequent videos on general relativity.